Okay. So good evening. Welcome to the 7th lecture. And today we're gonna shift gears. So first I'll make some announcements. Try to use the discussion boards as usual. Try to give feedback on each lecture if possible. Some of you have already given some feedback about the previous lecture, so as well as the assignment, so that's good. So project first report is due on March 1st, which is 1 week from now. And the second assignment, I was originally planning to give it today, but it overlaps with the project's last, since next week is the deadline for the first report, we will shift the assignment to by 1 week, basically. And the in-class exam will also be shifted by 1 week. So if somebody has issues, come talk to me or send me an email later. Okay. So in terms of
will you be providing solutions for the first homework assignment?
We are going through them, so we can actually, but it's not guaranteed. Okay, so today we're going to really shift gears and look at a very, very different technique or a class of techniques which are called graphical models in which should be an interesting tool in your toolkit. So, and then the next topic after this series of 3 lectures would be reinforcement learning, which is another thing which is closely related to decision making, sequential decision making, and so on. So that is another thing that is will be of interest to you guys. Okay. So, and we'll also spend potentially one of the lectures trying to look at some types of questions which will come in. So maybe not the whole class, but some part of it. As well as actually assignment 2 will be more less computational. So hopefully you'll get a flavor of how the exam will look like. Okay. And so coming a couple of points about the project. Project is 45% of this grade. So, and compared to that, assignment 1 was 15%. So you need to at least have 3x more effort in the project. So it cannot be one of the questions of your assignment 1, right? It cannot be just the last question of your assignment 1, for example. So you need to pace yourself so there are no last minute issues that your code is not running, you don't have enough compute power, or you have bugs but you've written the software or whatever is your deliverable. Okay, so a couple of additional points. There's this link which has some additional data sets if somebody has not yet still decided of what project they're going to pursue. And there's also, I think, the previous couple of lectures I pointed out a couple of challenges that are running this year. So one of them is the REXIS challenge. REXIS stands for Recommender Systems. So here I think they have some data set related to job seeker profiles and recruiter profiles, and they're trying to come with a recommender system. So you can look at that URL for more details. So today we're going to actually go at a slow pace. So actually this will be reminiscent to the first lecture. We're going to not review the things that we did last week, which was word-to-vec, word embedding, and applications of RNNs. So this lecture, we're going to get straight into some review of probability and some review of graphs. Very, very, very elementary stuff, but still it's good to have all of us on the same page. And then we'll look at directed graphical models and undirected graphical models. Okay. So how many of you have actually taken a course on probability, undergrad probability, let's say applied probability, in the past couple of years, let's say? Okay. So for most of you it will be a review, but still we'll go slow. So how many of you don't recall anything about probability or statistics? Just one? I'm sure there are more. I don't know why people are not responding, because see, it's in the class that you can actually pause and ask the instructor. In a real time exam, you'll not be able to think about this more carefully. So anyway, so we'll try to go slowly for this. So definitely ask questions if you're not clear about some concept. So what's probability? So probability is an object which is basically a bunch of numbers. So we use probabilities to represent beliefs about the state of the world. Okay, and so there's a formal calculus for manipulating uncertainties represented with probabilities, and actually it has a really rich formal history. So there's something called Cox axioms that you can go look into, where there are certain properties that beliefs should satisfy, and probabilities satisfy those axioms. Okay, at least our framework of the probability that we're going to use. Okay, so let's actually jump into an example, and we'll introduce some jargon on the way. So first thing is an outcome space. So outcome space just specifies the possible outcomes that we would like to reason about. So our world, for example, in the first outcome space is just coins faces. Okay, and in the second example, our world is just the outcomes of a die. Okay, a 6-face die. So this is our world. When I said we want to assign numbers to the states of the world, for us this is the world or that is the world in this example. We specify a probability which is a number to an outcome. So the outcome space has certain elements, right? It's a set. So you can assign a number to each element of that set such that the numbers that you assign are greater than 0 and they also sum up to 1. For example, you can assign 0.6 to the first outcome and 0.4 to the second outcome. So next, so what's an event? An event is a subset of the outcome space. For example, here the event is the outcome being even, and the second event is the outcome being odd. Okay, and the probability of an event is given by the sum of the probabilities of the outcomes it contains. So here it's quite simple. It's just the addition of the 3 outcomes that the event encodes. So for example, it could be 1/2 if it's a fair die. Okay. So next we'll introduce what is called random variables. So random variables also represent outcomes or states of the world, but typically they map events to numbers. Okay. So, and we'll use this notation where capital letter represents the random variable and realization of it to be a lowercase letter. Okay. Sample space we have already discussed. It's the outcome space. And probability mass function also we have discussed. It assigns a non-negative number such that it sums to 1. So for discrete outcomes, it's a summation. For continuous outcomes, it's a integral. Okay. Okay. So given random variables, assigning probability, which is a function which maps a random variable's realization or an event to a number, and the outcome space. So the next step is to kind of define what is known as expectation. So expectation of a function is written as in this form that we have actually used in some of our previous lectures, and it's just this summation over all outcomes, the probability of that outcome times the function evaluated at that outcome value. Okay, and so mean is this, and if you have a different function, so here the function is just identity function, and if you have a different function here, for example, x minus expectation of x square, then it's a variance. But you can also have other functions, and in fact you might have seen something called moments. Moments are just expectations of a higher order power. So if you have to the power 3 or 4 or 5, those are called moments, and there are something called centralized moments and raw moments. So that you might have seen in previous classes. And one of the things that you may or may not know is that if you know all order moments, then it completely characterizes the distribution of your random variable. Okay. So I mean, we are just going to accept it as a fact, but this is a non-trivial. I mean, whatever we have said till now is just some definitions, right? But this is saying that if you knew all the moments of a random variable, then you are characterizing the distribution of the random variable. Okay. Yeah. I mean, yeah. Here is the expectation of any arbitrary function. Here it's the expectation of the random variable itself. Yeah, it's the same. Okay. Any other question? Okay. So next we'll consider what is called joint probability. So joint probability is essentially a function of multiple random variables. So it assigns a number to realizations of multiple random variables. So for example, here the key concept being that two or more random variables may interact, and thus the probability of one taking a certain value depends on what other random variables are taking, what other random variables values that the other ones are taking. Okay, so joint probability is nothing but just this, like probability of x, capital X taking a value x and capital Y taking a value y is a number, right? In this diagram, it's actually a 3D tensor, and each cell corresponds to the probability of the three random variables taking a particular configuration, right? A particular set of numbers. Is that clear? Okay, I mean, it should be clear at least till this point. And next, we'll try to use some, build on top of that. Okay, so the first, new object or new thing that we're going to look at is conditional probability. So if you know that some event has occurred, then it changes our belief about the probability of some other events. So I'm using events and random variables interchangeably. So random variables are just functions of events. So if the outcome was tail, the random variable can be equal to 1. If the outcome was head, let's say the random variable was equal to 0. So that's the relation between events and random variables. Okay. So a conditional probability is just knowing that some, let's say in this case, z has taken a particular, so the event corresponding to the random variable z has occurred. Okay, and so let's say z took some value. In this case, let's say z is 1, 2, 3, 4, 5, 6. So let's say z took the value 4. Then the conditional probability is just the probability of xy given that z has taken the value 4. Okay, or here there is no z. I mean, here let's say if you have two random variables, and the conditional probability of x given y is just I mean, to get the probability, you have to divide with the probability of the event that probability of y that has occurred. But this is the notion of conditional probability. Any questions here? So I think in the die example, so you can think of events which correspond to whether the dice outcome was odd or even, and then you can also have an event which corresponds to whether the dice outcome was less than 3 or greater than 3. Then you can condition on one of the random variables which kind of represents whether the odd event occurred or the even event occurred. So condition on that, let's say odd occurred. What is the probability of the dice output being less than 3? That changes. If the event did not occur, there's a particular probability. But when the event occurs, there's a particular probability. Maybe it's the same as before, but you can condition that way. Okay. So the second interesting quantity is what is called marginal probability. So it's basically if you have a probability function defined over two random variables, and you want to get the probability of one random variable, then it's just you kind of sum or integrate over all the values of other random variables, right? So probability of y, let's say, is just the sum over all values that x can take. Let's say x is binary random variable. Let's say it takes a value 0 or 1. Then it's just the probability of x is equal to x, and this is the same thing. So basically, just take the sum over values that you don't care about. Okay, and this is like adding slices of the table together. So it's basically like squishing. Okay, so you can squish in either any of the three directions. I think in this case we squished around the z direction. Okay, so yeah. So next is the Bayes rule. So how many of you have heard of Bayes rule? Okay, so everybody follows this. So it's basically probability of random variable x given y is the probability of y given x times probability of x divided by the probability of y itself, where probability of y is the sum over all all realizations of x and the conditional probability of y given x. Okay. So basically, you can just if you had to deal with this, you can kind of work with this as well, basically. There's also another interesting rule that you need to know, which is the chain rule, which is if you're given a joint probability, okay, then you can factorize it into potentially if you have k terms and maybe k minus you'll have k terms. So where you can condition on all the terms that did not okay. Let me explain it by an example. Let's say probability of x, y, and z is just the probability of, let's say, x given y and z times probability of y, z. Okay, and then this you can further expand as probability of y given z times probability of. So this is just chain rule. Okay. So how many of you are familiar with these two, because these are kind of relevant? Bayes rule and chain rule. Okay, so next we'll look at what is called conditional independence. So here it's basically or in general independence. So let's kind of focus on this this aspect of independence. So two variables are independent if and only if their joint probability factorizes into their marginal probabilities. Okay, so this was actually the marginal probability that we saw a couple of slides ago. So you want this relation to hold. Probability of xy is equal to probability of x times probability of y. So graphically, if you think of xy as taking discrete values, let's say, then let's say. Then you can represent it as a table. Then all it's saying is, or a matrix. Then all it's saying is that this matrix is actually like a rank 1. You can decompose this matrix into two one-dimensional vectors. Okay, so two vectors. Sorry. And conditional independence is the same as independence, except that when you condition on one of the variables, then you have this product form rather than by itself. Okay. So that notation, if you condition on a variable, then the variable comes on the right hand side of a perpendicular symbol, and so it's basically, if you can see that this part is the same. It's just p of x comma y is just p of x times p of y, but everything is conditioned on the event z, and this has to hold for all z. Okay, let's actually kind of one small tangent. So what are independent event examples in real life, or approximately independent because this is all a model, a framework, so it doesn't really reflect real life. So for example, hardware failure events in different data centers you can think of them as independent events. And for example, any example that you come up with, it's hard to try not to have a causal relationship or an effect for two different outcomes. But for example, dependent events, you can actually have lots of examples. For example, what's the current news right now, and what are the queries being typed into a search engine? Same thing with news and let's say tweets, and then email communications versus the current state of affairs in your company. So those are all examples of events, and some of them are dependent, some of them are independent. Okay. Back to the die example. So we looked at independence in terms of the random variables, but independence, since as I said, random variables are just functions of events. You can directly look at this in terms of events themselves. So probability of A intersection B. So events are sets of outcomes, right? From 4 slides ago. So the probability that the number that you assign for the event A intersection B is going to be equal to the two numbers that you assign to individual events, their product. Okay. So that's definition of what does it mean for two events to be independent. Okay. And so you can ask whether these two events are independent. Actually, in this case, they are not, because the intersection of these two events is 0, right? And well, the product is, if it's a fair die, then it's going to be 1 by 6 each one. So that's why it's 1 by 6 to the power 2. And so you see that 0 is not equal to that, and so those two events are not independent. Okay. So let's say we have another. We kind of augment or expand our world or expand our outcome space to include the process of 2 dies instead of 1. Then we have, instead of 6 outcomes, we have 36 outcomes, and the probability distribution such that each die is independent. So probability of getting 1 on the first die and 1 on the second die is the same as the product of the probabilities. Okay. And let's say similarly for other pairs of outcomes. Then we can see that if you pick a so that you can actually just see by defining event A and event B in this augmented outcome space, and just trying to look at the intersection of A and B and trying to see that is in fact equal to the product. Okay, and that's true for every pair. Let's say 1s for this one and 2s for that one. Okay. Okay. So now let's just relate these quantities, expectation, conditional probability, marginal probability, joint probability, Bayes rule, all these to statistics. So probability is all about inferring probabilistic quantities for data given a fixed model. So you've already been given a joint distribution roughly, or some numbers that you've already assigned to events, and then you care about computing the marginal, computing the conditional, and so on, verifying independence and so on. Whereas statistics is about inferring the model, inferring the model given some data observations. For example, you can do clustering, classification, regression, and stats has many different approaches, but probability is just probability. Okay. So next, let's look at what is called the conditional probability table. So it's going to be relevant once you think of, okay, these are all just symbols that I'm thinking of right now, how to actually codify it. What is the what is it in terms of implementation? So the simplest thing you can do is for discrete or categorical random variables, the most basic parameterization is you just write down a table which lists what is the probability of xi equal to its kth value. Let's say xi is taking 10 values, then you just write down these 10 numbers, right? So that would be called a probability table. So that's acronym here, PT, and it needs to be, of course, as I said, our framework is such that we need these numbers to be non-negative and sum to 1. So for example, if the random variable is k array, which just means that it takes k values, then you have k minus 1 free parameters, right? Why is that true? Yeah, if you choose k minus 1 numbers, then basically the last number is fixed. Okay. So that's just the probability table, and what we care about is the conditional probability table. So it's very similar. So if discrete variable is conditioned on the values of some other discrete variables, we make one table for each possible setting of the parents or the things that we conditioned on, and these are conditional probability tables. Okay? It's basically essentially just the slice of this tree. For example, in this case. Okay. Is that clear? Okay. So let's look at what is the likelihood function. This at least we have not seen it in this class explicitly. You might have seen it in other classes. So what we care about is we have fixed data and we want to find parameters. So right now we've just focused on the probability function, which assigns a probability to any joint configuration of variables. So these 10-dimensional random variables or whatever 100-dimensional random variables, we can assign numbers to these configurations. And typically, unless you have some structure, you let's say each coordinate of this random variable takes 2 values. Then if you have a 10-dimensional 10 such random variables, then you need 2 to the power 10 minus 1 roughly 2 to the power 10 minus 1 numbers to actually represent that probability table, right? So you could kind of reduce the numbers by having a parameter roughly. Okay. In likelihood function, you kind of ask the reverse question, that if you had some data about these configurations, can I infer what is the parameter that governs these occurrences of these configurations, right? Probability is all about the chance of such a configuration occurring, right? So basically, it's as simple as probability of x given theta is a function of theta for a fixed x, which is the probability of seeing a configuration x given the current parameter theta. Okay. And so likelihood function is just that, and the log likelihood is logarithm of that. And if you choose to minimize theta, choose theta to either maximize the likelihood. Okay, in this case, if you choose theta to try to maximize the likelihood, then it's basically the maximum likelihood procedure, estimation procedure of estimating theta, which characterizes your probability table. Or you can kind of capture some notion of prior, and then you'll be essentially doing maximum a posteriori estimation. Okay. So are these concepts familiar to you guys from some other classes? Huh? This one is not clear. So these are just, so you must have done maximum likelihood estimation of parameters of simple one-dimensional continuous or discrete random variables, right? Like maximum likelihood estimation of, let's say, the bias of a coin. So you see, you flip the coin, let's say 100 times, it comes up heads 45 number of times, and let's say tails 55 number of times. Then you know how to kind of estimate the parameter, in this case the bias, using the data, right? So that's what. So basically, this is what you would solve. You would write down the probability of seeing these x's. If you assume independence, we'll get to the next slide. But you can kind of assign a probability given a particular bias. What is the probability of seeing 45 heads and 55 tails, let's say, and then you would try to change this bias such that the probability of seeing that particular sequence is high. Okay, so that's the maximum likelihood estimation in a nutshell. Who's not clear on this? If it's not clear, you definitely have to ask, because better use the time now than go to some other class and ask the same question later. Yeah. This one. Oh, it's just adding. You might have seen what is called regularizer, right? In other classes, sorry, in our own previous lectures. So you can think of this as some sort of prior. Okay. So I mean, here they're just calling it as penalized maximum likelihood, but yeah, this is just a function of if you had some prior belief on certain thetas being correct or not. I mean, more likely or not. Let's say you had a prior belief that your coin was fair, then you want to maybe impose that domain knowledge, and so that would be captured here. But formally, it's captured as this is just basically if you take off the logarithm part. So if you raise this term in terms of raise this term in a sense because there's a log operation happening here. Right? If you just undo that operation, you would get L of you get this, right? Probability of x, I guess given b. So that R additive term is actually just times e to the power, let's say R 3000. It's a multiplicative term, actually. So you can kind of map it to the prior that you've seen in the base rule. Okay. The denominator doesn't matter because it's not a function of. I mean, if you've seen base rule, right? Denominator is not a function of theta. So if you're thinking of optimizing for theta, then you don't care about the denominator. So you can interpret the second term to be something related to the prior. Okay, we'll not go into the details, so I'll skip that aspect. Okay, so a single observation of the data is rarely useful on its own. So generally, you have some number of data points, so 1 to let's say m. Then when you do statistics or when you do estimation of parameters, you typically assume, for example, that the observations are independent and identically distributed. Okay, which means that the same theta generated all my m examples. Okay, it was the same biased coin which led to heads in the first round, heads in the second round, or whatever, tails in the second round, and so on. Okay, and these are independent. So probability of seeing a heads in the first round versus probability of seeing a heads or tails in the second round. Those two random variables, they have to decompose as a product form, right? So that's what it means. Identically distributed is just that it's the same bias. Okay, and a second observation you typically make is you observe all the random variables in your which are relevant for your estimation. So that's what you do in machine learning, right? That's what you do in estimation or statistics. Okay, or more, I guess, in terms of equation. When I say IID data, you're just having a product form here. Okay, forget about if you can ignore the conditioning, right? We just saw conditional probability, so you can ignore the conditioning to interpret this. So probability of a particular data, seeing m data points, is just the probability of seeing the first data point as being x, second data point being as x, and so on. So it's just the product of all those probabilities. Okay, so that's what independence means, and log likelihood is written that way. And maximum likelihood, as I said, is all about setting the parameters most likely to have generated the data that we saw. So given the data, you want to set the theta that kind of generates the data that is the most likely to generate the data. Any confusion here of what these terms are? Are you not sure what's happening? So actually, in today's lecture, or in this segment, we are not going to focus on, at least today, we are not going to focus on estimation. So we are not really interested in the statistics part. So our object of interest is joint probability, right? Joint distribution. And what can you do with the joint distribution? One thing is, if you had access to a joint distribution, maybe you can sample from it. Okay, maybe that's easy, maybe that's difficult. For example, if your joint distribution was a multivariate Gaussian, maybe you can invoke a function and get a sample from that multivariate Gaussian distribution, right? The second thing is you can actually just compute the probability of a configuration, probability that x if it's a multivariate Gaussian, then maybe you can compute the probability that all the coordinates of your multivariate your random vector are, let's say, less than 0. Okay, you can compute the probability of that event, right? So with a joint distribution, you can compute probabilities of events, and you can also sample a realization. And you can also do a couple of other things, which is one of the key things, one of the keywords for this sequence of lectures is going to be inference, which is essentially what we've already seen. We have to compute the expectations of some variables, or we compute marginal probabilities, or we compute conditional probabilities. So these are just functions of your joint probability distribution, right? So that's the process that we call inference. And learning is what we saw in the previous slide, where you set the parameters of your joint distribution so that you kind of assign the highest score, or you can assign the highest confidence to certain data that has been observed. So for a given data, you want to figure out which parameters could have generated that data, and you want to figure that out. Okay, that's learning, or that's maximum likelihood estimation, or there are many other techniques, but that's the bucket they fall into. Okay, and so in the next lecture we're going to look at something called inference for us. Next, maybe 2 lectures down the line, we're going to look at learning, but for today we're going to focus on trying to manipulate the joint probability distribution. Okay. Okay. Next, let's quickly look at graphs. So how many of you have seen graphs technically? How many of you have not seen graphs at all? As in technically, like some jargon associated with the graphs, some properties of graphs, and so on. Okay, some people have not seen, right? Agree or disagree? No, in the sense, maybe in engineering or some other course, have you seen how graphs are, like, so for example, you're working on social network analysis or something like that, you might have dealt with graphs. So we are going to, and if you have taken, let's say, a course in computer science department or something like that, you might have dealt with graph algorithms and graph data structures. So we are not interested in all that. So we'll just kind of review some jargon associated with graphs. Okay. So graph is just a network. It has 2 kind of key entities. One is a set of edges, and other thing is a set of vertices. So graphs are heavily used in CS for algorithms and data structures, and here we'll only need some terminology, and the primary purpose, as we will see later for this lecture, is that graphs are useful for understanding the joint probability distribution. For us, as I said, we are interested in the joint probability so that we can compute expectations, conditionals, or marginals. So for that, graphs are kind of useful for manipulating this joint probability or understanding this joint probability. Okay. So I won't really draw a graph. So let's look at one category of graphs, which are called undirected graphs. So an undirected graph is basically a graph which is a bunch of nodes. So these are the nodes or vertices. These are the edges of the graph, right? And undirected just means that the edges don't have an orientation. So it's not a pointed arrow, right? It's just a straight line connecting 2 nodes, right? So that's what undirected graph means. Okay. So let's now look at some terms associated with an undirected graph. So first of all, when I draw a graph, there's going to be a bunch of vertices, right? So I'm going to enumerate them. So let's enumerate them as 1 to n. And then I'm going to call the size of the graph as the highest index. So I'm going to just call the size of the graph as n. And edge, to represent the edge, I'm going to just use the pair of nodes that it connects to. Okay. So if it's connecting node 3 and 4, then the edge is just indexed as 3, 4. And since the edges are undirected, this 3, 4 is not any different from 4, 3. It's the same thing. Okay. So the maximum number of edges in an n node graph is n times n minus 1 by 2. Is that clear? Why is that?
Each node is connected to n other than minus
Okay.
1.
Okay. What about? I mean, does everybody understand why the maximum number of edges in this undirected graph with n nodes is n times n minus 1 by 2? Or is it too simple? I just want to calibrate, right? Is it clear? I mean, if it's not clear, then it's always good to kind of draw a 3-node graph or a 4-node graph and see what is the maximum number of edges that you can fit and see if it is actually following this formula, right? And so if you have a graph, let's say here, you'll call node let's say 1 and 5 connected if there is a path as in a sequence of vertices with edges in between that kind of gets you from 1 to 5. Okay, so there's a path of edges between them, and a subgraph of G is just going to be if you kind of forget some of the vertices and the edges between them, then you get a subgraph. Okay. So to be more clear, what is a path? A path is just a sequence of vertices where each successive pair are connected by an edge. So for example, a path is just, for example here, a path can be 1, 4, 5, 2. Okay. In this case, a sequence of vertices, right? 1, 4, 5, 2, such that each successive pair, so 1, 4, 4, 5, 5, 2, are connected by an edge. So that 1, 4 is connected by an edge, 4, 5 is connected by an edge, 5, 2 is connected by an edge, right? So you can see that 3, 4, 5 is not a path because there is no edge between 3 and 4. Okay, and a subgraph is just let's say if you want to make a subgraph with just vertices 1, 2, and 3, then you're just gonna ignore 4 and 5 first of all. So all the edges, and you also remove the dangling edges. So the subgraph, which includes vertices 1, 2, and 3, would be just this part. Okay. The second function of a graph that we're going to look at, a function of vertices of a graph, is the notion of a neighbor. So neighbor is just all vertices that share an edge with the node. And they are denoted by I'm using NBHT, or you can use any acronym of the node. Okay. So all vertices that share an edge with that node. Those are the neighbors. For example, 3, 4, and 2 are neighbors of 1 because there's an edge from 1 to 3, 1 to 4, 1 to 2. Okay. Is this clear? So path and neighbors and subgraph is clear, right? Okay. Now let's look at what are called cliques and independent sets. Okay. So what's a clique? So clique in a graph is just a set of vertices. Okay. So informally, they are all directly connected to each other. So these vertices should have edges between them. Okay. It's not a path that connects these vertices. It has to be edges between them. Yeah. No, if you have three vertices in a graph, how many edges can you put in there? It's counting. It's not about. I mean, it's related to what you said, but. Like one intuitive explanation was given by Abhishek. Okay, he said for every node, you potentially can have n minus 1 neighbors. Right? So you just put the nodes. You have a graph. You start from one node. You see how many neighbors can that node have. Like how many edges can I generate from that node, right? choosing 2 points out of n points, yes, that is true. Number of ways of choosing 2 points, yes. Yeah, that is what it is. So if you have n points, number of ways of choosing 2 points is these many. Right? Yes. No, n choose 2 is also this. Okay. Divide by 2 is, if you go by his logic, because I'm considering every node and n minus times n, and because there is symmetry, I just divide by 2. So a clique in a graph is a set of vertices that are all directly connected to each other, and formally it's basically a subgraph which is complete. Complete just means that if you kind of look at the subgraph, every vertex is connected to every other vertex. Okay. So for example, an edge is a clique of just 2 vertices. Okay. So let's say, what are the cliques present in this graph? Huh? Yeah, all the edges are the cliques present in this graph. Okay. So you don't have any interesting cliques here, but let's say you made a graph with 4 vertices, okay, and you had n times n minus 1 by 2 edges, like 6 edges here. Then that would be a clique, okay, because that would be a clique in a sense. That would be a clique of size 4, because if you think of if I take all these 4 vertices, then every pair of vertices in this subgraph has an edge between them. So that's why it's called a clique. Okay. Yeah.
This 1, 3, 4 is not
1, 3, 4 is not a clique because there's no edge here. If there was an edge, then yeah, 1, 3, 4 would be a clique here. Okay.
But when we are saying like in this 1, 2, 3 are there,
Yeah.
so it shouldn't be only 1, 2, 5, 4.
No, even 1, 2, 5, 4 is not a clique. So in this graph, actually, there's just 2 cliques. So just every edge is a clique. So pairs 1, 3, 1, 4, 1, 2, 1, 2, 4, 2, 5. Sorry. Huh? Yeah, the number of edges is the number of cliques here. 2 cliques as in just 2 element cliques. Yeah, size 2, sorry. Okay. And what is an independent set? Okay. Independent set is a set of vertices whose induced subgraph is empty. So there is no edges. So if you pick a bunch of vertices from your original graph, and because it's a subgraph, you have to eliminate everything else, right? But then you'll see that there is no edges between any pair of vertices here. Then that's an independent set. Okay. So for example, in this graph, this is a clique, right? Because for these four vertices or nodes, every pair of vertices has an edge between them. And if you just pick things which are not connected, for example, if I just pick these 2 vertices and get a subgraph, then I'll have to delete all these vertices, and so I'll have to delete all the edges. So there is no edge between this subset, and so that's an independent set. Okay, they're just 2 new concepts, relatively new concepts that you might not have seen. And then there's the notion of maximum clique or independent set, which is the largest in the graph. For example, you can offline try to compute what is the largest independent set here. Okay, and also what is the largest? The largest clique is kind of easy to see. It's just this 4 vertex clique. Okay. You can also, there is something called maximal clique, where you can't so let's say there's a clique where you have some number of vertices. You can't increase the number of vertices easily in that clique. Okay, then it's called a maximal clique. For example, if I chose these 3 nodes, okay, that's a clique, right? Because if these 3 nodes are there, then there is an edge between every pair of nodes in that set. But I can't add any other node, because adding any other node will not give me a bigger clique. right? Then that clique would be called a maximal clique. It's just a definition so far. All of these are definitions actually. It's just like so independent set is just a set of vertices. Okay, so given a graph, I can just pick a bunch of vertices, right, and get a subgraph, right. So if the subgraph is such that every node has no edges, then it's an independent set. So let's say I have that. Let's say I have a graph like this. Okay. This is not a clique, right? I don't have the full additional two edges there. So let's say I picked this node and this node. Okay, I'm creating a subgraph. When I say I'm creating a subgraph, I have to delete these other nodes, other vertices, right? When I delete other vertices, these are dangling edges, so I'll have to delete them as well. And then what am I left with is just these two, right? So these two don't have an edge across them, so this is called an independent set. Let's say my original graph had something like this, and I chose these two. Then this edge would remain in that subgraph, and then it would not be an independent set. You can do this for arbitrary graphs. I mean, okay, computing independent sets is you can compute it greedily, and then there's optimization versions of it which are hard and so on. Okay.
What is maximum?
Maximum is just this is one independent set. Maybe if I could, I mean in this case you can't, but if I could have had three vertices, then that would be a larger sized independent set, right? For example, in this, what is the largest independent set? It's definitely not 2, right? I could just greedily pick this, maybe this and that. That would be an independent set of size 4. So I don't know what's the largest independent set size here, but yeah, that's what maximum independent set means. Maximal just means if you greedily do something and you can't add an additional node and still maintain the independent set property, that there is no edge between the vertices in that set, vertices in that subgraph, then that would be called a maximal independent set. Okay. Okay, so that's about undirected graphs. So let's look at directed graphs, and in particular directed acyclic graphs. Okay. So what is a directed graph? It's basically having additional metadata. Okay. So metadata is this. I just have directions or orientations. So basically, you have edge uv. It means that there is the edge is originating from the node u or vertex u and going to vertex v or node v. Okay. So in this graph, you can actually have an edge uv, and you can also have an edge vu, and they're going to be different. Is that clear? And it can capture asymmetric relations. For example, in social networks, there could be a symmetric relationship, right? Even in Twitter network, for example, there could be a celebrity, and then you may have an edge. If you're following them, you may have an edge from you to them, but they may not have an edge back. Okay. So directed graph is just having orientations, additional metadata, and if you have a directed acyclic graph, it means you don't have any directed cycles. Okay. What do I mean by that? For example, if I add directions to this graph, let's say something like this. Then, okay, actually I'm doing cycles, but okay, I have a cycle here, right? I can start from this node, let's say node x. I can go to node, let's say x1, x2, x3, and x4. Then I can actually go from x1 in the direction of the edge, in the direction of edge, in the direction of the next edge, in the direction of the next edge, and actually get back to the original node. So that's what you would call a directed cycle. Okay. A cycle is just a path where the starting point is the ending point. Okay. So directed acyclic graph will not have something like this. Will not have edges which will let you get back to the node. Okay, it will necessarily have to have things where you don't end up back to the same node for all whatever nodes there are in that graph. Okay. So, for example, this is a directed acyclic graph, right? Yeah. This is a directed acyclic graph. Is that clear? Why this is a directed acyclic graph? Okay. So now let's look at path. We saw the definition of a path earlier, I think, the notion of a path. So there are two paths, two types of paths in a directed acyclic graph. So first is the same as before, so same as undirected graph, where you kind of ignore the metadata. So ignore the direction of the edges. And for example, in this case, you have a path from 3 to 1 to 2. So you have a path from 3 to 2. Okay, right? Because you can get to 2 by going to 1 and then going to 2. Directed path is where you have this additional metadata, and therefore you have a constraint that you are supposed to take direction into account. So for example, 5 to 4 to 1 to 3 is a directed path. Okay, so you don't have a directed path from let's say 3 to 2 because you can't go to 1 because the orientation is against you, right? Okay, those are just paths and directed paths. So in directed graphs, there's this notion of family. So let's now look at the notion of parents. So parents of a node, so a node or a vertex, parents of a node J are denoted by PA of J, and they're just simply the vertices which are connecting, which are directing to this node. Okay. For example, the parents of C are just A and B because A has a direct link to C, B has a direct link to C, and they have an edge, right? Whose orientation is to C. Okay. So basically, essentially, or more formally, it's neighbors of that vertex that point to that vertex. So, is it necessary to have just two parents, by the way? Okay. You can have 1 or 3 or 4 or whatever. And so, parents of A, it's just a function, right? So, if A doesn't have any neighbor with an edge pointing to them, then it's an empty set. And in this graph, for example, parent of 4 is going to be just x3, one parent. Okay. Then similar to parents, there is this analogous notion of descendants. So who are descendants of a node? All nodes that can be reached by following the arrow directions. So all nodes that can be reached from that node by following the arrow directions are descendants. So in the below graph, for example, descendants of A are C and D. Okay. So it's not. So descendants is not about just one hop. Actually, even for parents, you can talk about ancestors and so on. But I guess that's why we didn't use the word children. We use descendants because you can go multi-hop. Okay. So descendants of x3 is just going to be x4. So this should be quite clear. Okay. So next, let's look at the notion of connected graphs. Yeah.
What be a descendant of itself in a cyclic case?
In the cyclic case, yeah, if you can.
Directed cyclic case, what can be descendant of itself?
Yeah, it can be. Yeah.
Is that
Maybe the notion of descendants doesn't make sense for cyclic graphs, directed cyclic graphs, but you can redefine that you will not include the same person in your descendants. So. Okay. Any other question at this point? Okay. So next, let's look at this notion of connectedness. This you might have seen if you have done some social network analysis again. So G can be either a directed or an undirected graph, and it's connected if there is a path between any two vertices in that graph. So pick any two vertices, and if you can find a path between them, then that graph is called connected. Okay. if you can't find, like say you picked two nodes and you couldn't find a path which gets from the first node to the second node, then you may have something called connected components. You may not have a connected graph. Or in the notion of connected components, you would have a connected graph if you just have one connected component, right? But if you can't get from, let's say, two vertices I to j, then you may have multiple connected components. So it's basically subgraphs determined by mutual connectivity. Okay. So the graph on the left is a connected graph. The graph, this is an undirected graph, which is not connected. Okay. There is no path from this node to any of these nodes. So in this case, you can say that you have two connected components, or essentially two subgraphs. Okay. Is that clear?
How is the first one a connected graph? We cannot reach the final node. If you start from any of that, we cannot reach the.
Oh, it's from here?
Yeah, if you start from, you cannot reach the.
No, it's just we are asking for a path, not a directed path. Yeah, I mean, I'm just saying ignore the metadata, which is the direction information. We're just asking for ignore the direction information. Can you get from a node to another node? And a complete graph is essentially an edge between all pairs of vertices. Yeah.
Undirected graph will always be connected.
No, this is an undirected graph, which is not always connected.
So the system is not connected.
No, there's no edge. There's no path from this node to this node. Right?
You can have a vertex which is not connected.
Yeah. You can have not just vertex, right? You can have two separate triangles. Let's say, right? Let's say this was. I guess this is kind of easy, but and let's say there was something like this. Okay, 5 nodes in this graph. Okay, this is one graph, 5 nodes, except there are no edges between this side and that side. And okay, so very close to the notion of connectedness is something called singly connected, which just means that there's no more than one path between them. So when you don't have more than one path between any pair of vertices, then it's called singly connected or just a tree. Okay. So a tree. So I mean, if you use random forest, you should know what a tree is, or a decision tree actually. So you just have one path from any pair of nodes, basically. And if you have more than one path, then you just call it multiply connected, or you call that graph a loopy graph. Okay. I mean, and these definitions are not particularly for directed graphs. You can use that for undirected graphs as well. No, I mean, if you ignore the metadata, this is the undirected graph, right? If you ignore the direction information, the path from C to D can be C to A to B and C to F to D.
It will always be.
It will always be? No. I mean, you can get rid of metadata here and it would be a tree, which is undirected, right? So this should be a regular tree that you've seen. Yeah. Okay. So that's a review of some subset or some jargon related to probability and some jargon related to graphs that we will probably use in the next couple of topics. So the first topic is going to be directed graphical models. Okay. So we're going to look at. So I've just used the acronym DPGM for directed probabilistic graphical model. It's also called something. It's also called or popularly called Bayesian network or a belief network. Okay. So if you have come across somebody who says, "Oh, I've used BayesNet for some project," all they're talking about is they'll use directed probabilistic graphical model. Okay. In fact, actually, there is nothing Bayesian in this framework. You can add Bayesian elements as you want because you can always extend a framework or extend the basic concepts, right? But It's just historically it's called a Bayesian network, but you can just think of it as trying to kind of use directed acyclic graphs to understand joint probability. Okay, and understand joint probability and ultimately compute your marginals, conditional probabilities, and expectations. Okay, so these can actually be called conditional independence diagrams, and we'll get to why these can be called conditional independence diagrams in a few slides. Okay, in fact, we want to call them this because, as we will see, the graphs will try to encode some conditional independence properties of the joint distribution. Okay, you have a joint probability distribution, and you have a graph which somehow captures the conditional probability, so conditional independence properties, which are honored by the vertices of the which are honored by the random variables of your joint probability distribution. Okay. Okay, so what's the key idea in directed probabilistic graphical models? The idea is about factorization. So factorization, we've already seen one type of factorization earlier, which was for any joint distribution, you can easily just factorize it by just reapplying essentially Bayes rule, right? Conditional probability times the probability of the remaining variables, right? Probability of x is equal to a. Y is equal to b, and b is equal to c. You can just write this probability of x given y comma z times probability of say y given z times probability of z. So this is just a factorization. But even a graphical model or a graphical model framework, when we use graphs, they'll also give us some factorization of my joint probability distribution. Okay, but it will be more interesting than just this degenerate factorization. In fact, this is not unique, right? I could have chosen any other. I could have chosen probability of y given xz times probability of x given z times probability of z, or some other sequence. So for us, graphs in this trying to the use of graphs will be to get factorizations, and firstly they will be used as a notational gadget to denote the joint probability distribution, and for visualizing, mostly for visualizing conditional independence properties, as we will see in the next few slides. And graphs can ultimately also be used for something called inference. I think a few slides ago I said what is inference, right? Inference is all about computing expectations, computing marginals, computing conditionals. Okay, those are just three broad categories. You could do other things with the joint probability distribution. So that would be the inference part. And there we'll see a popular technique called Markov chain Monte Carlo, okay, MCMC. But that's next lecture. So today we are just going to focus on visualization and trying to understand how does a DAG, in this case a directed acyclic graph, capture conditional independence properties in your joint probability distribution. Okay, so there are two notions of why we care about trying to capture conditional independence properties. Okay, one is written here. Okay, which is we want to do tractable inference. In a sense, if you have a let's say I have a joint probability distribution over 100 variables. Okay, 100 random variables. Okay, it's not that big, right? 100 random variables is not too much. Let's say each random variable is just binary. Okay, it's just a flip of a coin essentially. Okay, then if you think of the probability table, then how many numbers do you need? It's just I guess to the power 100 minus 1 or something. Okay, these are the numbers you need to kind of encode this joint probability distribution in this discrete case. And then let's say you want to compute probability of x1, okay, or probability of x1 is equal to something. Then you just have to do the summation, right? You have to sum over all x2 to x100, taking all these values of the joint probability. Right? we have to do this, and so this has this actually is a quite a complicated summation. Okay, it has too many terms, by the way. So what I'm trying to say is that if you knew that some of these random variables were conditionally independent or even independent or conditionally independent, then you can use that information to do this, for example, a marginal computation very fast. Okay, that's it. So that's the for example, let's say I knew that every random variable is conditionally independent of everything else except for the previous indexed random variable. Okay, let's say x100 is only is conditionally independent of everybody else given x99. Okay, and similarly I can do that. If I had that structure, then you can see that this is just very this some kind of you can pass it through and you can do a simple computation. We'll get to that example again later. Okay, but so for today, if you are not clear of why we are looking at conditional independence properties, it's for the next class where we use that to kind of get tractable inference methods to infer something. Now the second aspect of why we care about conditional independence, why do we care about a directed acyclic graph or a cyclic graph, is trying to understand your data, right? So we are in the domain where we don't care about at least we care about the joint distribution. So you know that classification regression is about conditional distribution, right? Condition probability of a class given my data. Okay, whereas you can think of today's object joint distribution being the probability of class and the data. Okay, probability of y equal to something and then x is equal to this is the joint distribution from which you can create the conditional distribution probability of y is equal to c given x is equal to some vector, right? X being some class given y is equal to x. So this would be an object of interest to you if you cared about classification or regression or something like that. Okay, but today our object of interest is this, and in particular, we are actually not even gonna learn or train anything. Assume that we have already been given these random variables and we have some notion of how they are related to each other. In the sense, I know that x1 is the probability of failure of a component in my multi-component circuit board. Then let's say x1 is the probability of failure. Then I know that if it fails, then it will affect a few other things. Okay, there is some domain knowledge, right? Let's say it's the power system, then it will affect maybe some other components. And there could be some other variables which affect some other things, right? So if I have that domain knowledge, then I can relate these random variables with each other. Okay, and then I would be interested in whether, okay, if some event happened, then are, let's say, two random variables of interest conditionally independent of each other or not. Okay, and we'll get to such examples later. But what I'm saying is, if you had domain knowledge which kind of relates these random variables, and let's say you also have the joint distribution, okay, but that's for later. Let's say we had some structure. Let's say x1 represented the probability of failure of something, x2 represented sprinkler turning on or something. Let's say in a maintenance system. Then, if you can encode domain knowledge that okay, if this happens and something else happens, and so on, then from that information, can you kind of use conditional independence properties? For example, condition on, for example, the alarm going off. Can you tell me what is the probability that it was caused by, let's say, the power system failing or something like that? So, for example, you can say condition on alarm going off. Are these two events independent? Let's say the first event is the power system failing. The second event is voltage increasing or something. Okay. Are those two events conditionally independent given that I've observed alarm going off? Let's say something like that. So conditional independence has some interpretability aspect to it, and that's why we're studying it. So let's ABC the random variables. So I'm going to acronym RVs for random variables, and we know that joint distribution can be factorized in a certain way, in any way. Okay. In this case, I've just chosen a particular factorization. Okay, and there's nothing unique about this. We can always do this. And so given that factorization, we're gonna try to construct a directed acyclic graph. Okay, so that's the first step. Okay, I factorize it in this way. I have 3 terms. So in every factorization, typically you'll have the number of terms will be the number of random variables. Okay, three random variables, 3 terms. So I'll create a node for each factor, and I'm gonna call the nodes on the left side, on the right side of this vertical bar, to be the parents of that node. Okay, so when I do that, I get this graph. Okay, so can you see that it has 3 nodes labeled A, B, and C, and since I factorize it in this way, C had parents A and B. So actually this red part kind of represents the edge of the arrow. Okay, in this diagram. Actually, later diagrams have a better picture. So this is from a module called Network X. I don't know if you guys have used Network X in Python. Okay, it's a very nice module that you can use just like Keras or other things that you've used to deal with graphs. Okay, you can add edges, add nodes, do computations on them. So here I'm just saying that for the first factor, so I'm just in the factorization I'm calling each term to be a factor, and I've just drawn an edge between the left side of the factor in that term and the right side of the factor. Okay, so there are 2 edges going into C, and then there's an edge going from A to B. Okay, that is this edge, and so there are 3 edges in this directed acyclic graph. Okay. And in particular, you can see that if I construct a graph like this, there are no cycles. You can't return back to the original node. Okay. But there's nothing special about this factorization, so we could have done some other factorization and we could have gotten some other directions, right? Some other direct-oriented edges. Okay. Now let's look at, let's say, I wanna impose an additional information that C is conditionally independent of B given A. Okay. So what does it mean in terms of notation? I'm going to use C. This is called the perpendicular symbol. So C is conditionally independent of B given A. That's what this kind of reads. Okay. So if C is conditionally independent given A, then probability of C given A comma B is probability of C given A. Okay, you get rid of the B. Okay, remember the conditional independence formula, right? Probability of is this clear or is it not clear? First of all, no. It's not clear. So we looked at conditional independence like at the beginning of the lecture, right? Everybody said they understand conditional independence. Okay, conditional independence just means probability of A. Okay, the vanilla version is actually just probability of A given A comma B given C. It's just probability of, it's just additional vertical bar and additional C here. Okay, so it's just probability of A given C. And it's probability of B given C, right? So that is the definition of conditional independence. But if C is conditionally independent of B given A, then no matter what value B takes, the probability of C doesn't change. So I can eliminate B from the right hand side. That's what I've done here. Okay. So what I'm saying is what we've done is we have A in the right hand side of this vertical bar, which means that we have condition on A. But condition on A, C is independent of B. Okay. So we have used that other formula, right? Probability of C given B is equal to probability of C. This was actually an alternate definition for independence, right? I mean, we had a definition of independence which said probability of C comma B is equal to probability of C times probability of B. So I'm using, actually these are lowercase things, okay? Probability of capital C taking a value small c and so on. So this is what we saw. This is what is independence. This is also an equivalent definition for independence. No matter what B, whether B has occurred or what value random variable B has taken, it doesn't influence the probability of C. Okay, for any of the C values that we can take. So that's what we have used here. So probability of C given A comma B is probability of C given A. So if this is the term that we replace in that factorization, then I can get rid of one of the edges. The edge from B to C. Okay. Now I've gotten a different graph. So it's interesting, right? I made a conditional independence assumption on my joint distribution, on my total probability distribution over A, B, and C, and because of that, I got a different graph. Okay. Is that clear? So we just went from a distribution to a graph. We just made a rule that, okay, if I have a distribution, I'll arbitrarily split it out into a factorization. And if I have some conditional independence properties, then I'm going to delete those edges. Okay, that's a very ad hoc way, but still we went from a distribution to a graph, a directed acyclic graph, right? It's not clear. Okay. Let's go the other way. Let's go from a graph to a distribution. So what if we start from a graph? Okay. In particular, can we construct a particular? Can we construct a probability distribution? So let's start with this graph. Okay, which has 4 nodes, 4 vertices, and let's say the oriented edges are 3 in number, which are given as in this diagram. So from this diagram, I want to get to a probability distribution. Okay. So any ideas how to get from? Okay. Yes. So that's actually roughly the heuristic or the rule. So let's say we'll write one term per node. Okay. And there is no sequencing here. Let's pick node C. Okay. What are the incoming edges to C? Those are from A and B. So we'll just include a term which has C on the left side and A and B on the right side. Okay. And if they don't have any incoming edges, we'll just use P of A and P of B, because A and B don't have any incoming edges, and B has an incoming edge from C, so we'll write P of B given C. Okay. So given a graph, we were able to generate a particular factorization. Okay. But it's not clear whether this first of all is a distribution. But anyway. Yeah, I mean, so the rule was, it's just a rule, but the rule was that for every node we'll write a factor. Okay. So when there is no parent, then it's basically like, I guess you can think of it as a shorthand for P of A given parents of A. Parents of A is just 5, so P of A given 5. That's what that is. You can ignore the 5 thing and. First of all, so if I just write it this way, okay, these are all these are conditionals, these are marginals, right? If I had a joint distribution, these two would be the conditionals and these would be the marginal, right? It's not clear that their product is actually, you can multiply it this way, and maybe you can multiply that for every configuration of A, B, C, D. It's not clear that would actually give me a valid joint distribution. Because we went from a graph to a probability distribution. Okay. But it's okay. We'll get to that point whether this is a valid distribution or not a bit later. So now let's kind of define something, okay, some relationship between graphs, directed acyclic graphs, and so I just defined, so I said our algorithm or rule is I'll look at every node in my directed acyclic graph, and for every node I'm just gonna write the nodes realization on the left side of my factor and the parents on the right side of the factor, right? That's why I got 4 factors, right? Now I said this, I'm going to equate this product to be equal to, I'm just going to define this product to be equal to the probability of A, B, C, D. The random variable A taking value small case a and so on, lowercase a and so on, right? Now this product was generated from this graph. So this product, let's say from that product I defined this joint, okay, for a particular configuration or particular realization. This quantity may not be a valid distribution, in the sense it may not sum up to 1 if I add up over all A's, all B's, all C's, and all D's. Because I went from a graph to a definition for the joint probability. Is it obvious that it can sum up to 1? Because it's not obvious. Because if you go from the other direction, right? This we know because if joint probability is from a joint probability we are going to a factored form. I know that if I sum over all A, B, and C, this is equal to 1 on the left side. So I know that this particular product of 3 terms, if I sum over A, B, and C, it's equal to 1. And there was a graph interpretation, but that's inconsequential. But to this discussion, so here, if I have this product, these set of factors, whether these factors actually lead to probability for a configuration such that I sum over all the A's, B's, C's, and D's, will it give 1 or not? It's not clear. No, if I go from here to here, in fact, I will not get this factorization at all, right? Forget about this graph and this particular way of constructing factors. Let's say I wanted to, from what we know up till this time, up to now, if I want to factorize this, I only know one thing, which is chain rule. So I can do probability of A given BCD times probability of B given CD times probability of C given D times probability of D. Those are the types of products I can get. This is not that, right? None of the factors has three terms on the right side. Okay. No, I just don't have any metadata other than direction and connection between two random variables. So probably, we are just focusing on that there are these number of random variables, and if there is a factorization, we are just representing that as a graph. Okay, we are trying to represent that as a graph. That's what we did past couple of slides when we said, okay, if I factorize it this way, I'm going to get a certain graph. If I factorize it in a certain other way, I'll get some other graph. Or actually, if I assume conditional independence, then I'll get a graph with one less edge or something like that. That's what we saw in the previous couple of slides. Here we are saying if I had a graph and I wanted to imagine what a factorized version of that joint distribution would look like, I'm proposing a candidate which was this for this graph. Okay, and it's not clear that it is actually leading to a valid joint distribution, but we'll get to that maybe a couple of slides later. Yeah, given an ABCD, it spits out a number. No, I mean, the right side, these are conditional functions, right? These are, if you had a joint distribution, let's say through joint. Where is that? This is probability of D just given C, that's it. No, there is no chain rule here. We just looked at the graph and created a bunch of products. if we had applied chain rule, then as you were saying, we would have gotten probability of B given A comma B comma C times probability of let's say C given AB times probability of A given B, let's say, and times probability of B. This would be the vanilla factorization, right? If you went from a joint distributions to this would be one valid factorization. Is that confusing or is it clear? I think if it's not clear to the front of the group, then it's definitely not clear on the back side. Okay, let's break at this point. If you have questions, please come up front. Yeah, the break is for 5 minutes. Yeah.
How do you draw that graph? Like there should be some basis of drawing that graph.
Yeah, we'll get to that. Right now, we're just trying to imagine if I had a joint distribution, I can draw a graph according to some rule. And if I had a graph, I'm just defining a rule to create a product.
So if we draw it using some basis, then when we write down the joint distribution, it should somehow.
No, what was the we know that for this factorization it's fine because this is actually just probability of A comma B comma C comma D.
Yeah.
But for this, it's not clear, right? How can you get? It's not. It's fact. This is not equal to
I'm
that.
saying that if let us say for this one, like we are drawing this graph on certain basis.
No, this is arbitrary. I could have changed. We have just drawn some graph.
So then why are we even deriving the joint distribution? Like what are we trying to even find?
We are trying to relate a graph to a joint
And
distribution.
what is the source of this graph?
Domain knowledge. I mean, the graph is supposed to capture the joint distribution. Okay.
Yeah.
Ultimately,
So,
but here we have just said, okay, if I have a graph, I can just create these factors. Can I define a valid joint distribution or not? That's the question that's the line of thought.
so for constructing such a graph, we
Yeah.
use the domain knowledge, right?
Wait. So let's say this was the input.
No, I'm asking in general if we have a graph, to construct that graph, we use a lot of domain knowledge.
Yes,
to
yes,
construct
yes.
So now if you're tracing back from the graph to the joint distribution, it should sum up.
No, joint distribution has nothing to do with domain knowledge, right? Like I can say random variable A is related to random variable C in this way.
Yeah.
Let's say A is something failing and C is alarm going off. Yeah, they are related in this way. How is that going to tell you that the joint distribution is valid or not? Valid means sum up to 1 and things like that. It's not clear, right? It's just showing potentially causal relationships. Potentially causal because sometimes there could be errors, but erroneous interpretations. But roughly that's the information. That's the domain knowledge on the graph.
So in that case, any graph cannot be tied back to a joint distribution. Can I assume that? Or there are certain graphs which can be tied back?
No. For every graph, you can define a joint distribution.
But then it may
but
not
what
be
is it?
valid, or it can be
It
valid.
will be valid, but as you will see later.
But not something more.
But the graph kind of assumes something which your
Different
real
from-
data may not. We'll see that the graph will assume conditional independence stuff. That's why we were talking about conditional independence a few times before. That assumption may not be true. So that's the relation.
So ultimately, will we depend on the graph, or like if the data is showing something and if the domain is showing something? So
See, think of it as this way, right? Your data is basically columns of your Excel sheet.
yeah.
You have like 10 columns, 10 random variables. They are all taking different values. Now, your additional domain knowledge would be which random variable is related to which one. Okay? That would potentially generate the graph. You don't need the columns or the actual joint distribution. But to create the joint distribution, you can actually create that, right? You can look at every probability of every configuration. You can actually create that.
But then if you're going through the data and you construct a graph,
No, we are not. Right? I said if you had metadata that which random variable talks about which random variable, that can be just domain expertise, right? I can say that a failure here will trigger an alarm.
Correct, but if the data is representing something else,
Uh,
there can be cases.
yeah, there are
like
two
that,
things, right? There's data and there's domain knowledge.
Yeah.
They are
so
not.
ultimately,
They're
what are we
complementary.
trying to do by connecting the graph to the
Capture conditional independence information.
like if there are n different factors that are controlling a particular event, then how is each of them?
I just gave you this example, right? Here I said if you want to represent this, you have 100 columns in the Excel sheet. If you want to represent this, you'll have. If you want to represent this probability, okay, you'll need these many
Correct.
numbers. For every configuration, you need to assign a number,
Yeah.
right? That's too big. But what if I said additional domain knowledge I gave you that x100 is independent of everybody else given x99.
So in that case, I mean, we'll join the data with the graphs and then come up with a distribution. Can I?
I have this
Yeah.
without domain information. Now I'm adding domain information that there is this conditional independent.
Yeah, through the graph.
I can even without a graph also I can say that, right? If it's conditional independent, can you tell me? I can create a factorization and deal with it.
Yeah, but you use
Graph
again
is
that,
for
that
visualization.
domain. Yeah, so you use that domain knowledge to build a graph.
Yeah. Conditional independence. Whether when I say that, you can visually look at it as a graph.
Okay, so we'll combine both data and conditional independence properties
Information, which is domain knowledge.
and then come up with something which is valid.
No, we can say if I have conditional information, then how would the graph look like? It's not clear, right? If I say things are conditionally independent, how will you create a graph? It's not.
So, I mean,
If you can encode the graph, then that can be used for whatever purposes you want later on. But it's not even clear how to represent conditional information, conditional independence information.
so imbibing conditional independent information on the present data to come
Yeah.
up with a graph.
No, from conditional information you get to the graph.
Yeah.
From the graph, you know how the joint distribution factorizes. If joint distribution factorizes in certain way, then inference is easy. Computing marginals, computing expectations is easy.
Okay, now I understood. I just wanted to know.
Yeah, that's the pipeline. That's the pipeline. Okay.
Just for the project.
Project discussions will take more time.
No, I know, but I can meet you tomorrow regarding this, right? Because I have actually, as you said, for recommendation and for reinforcement learning, I had to learn O2 course from David Silver.
Yes.
Yeah, so I've gone through that. I have certain issues with that. If I
We're
can,
gonna actually revisit the same thing in the last 3 lectures of this course.
this is my bad. So, anyways, so I have gone through that. So after that, I have a few questions in that. So if I can complete that shortly, and after that, I have understood how I ran the code, the Python code which was there in GitHub.
Yeah, it's not complicated. I mean, if you understand the
it doesn't seem
basics.
complicated.
Yeah.
I've gone through that. Some things are not very clear. I'll probably discuss that with you. And if I go through that, can I get some of the help from the TA for the code part if something is wrong? Because I'm having.
You can ask her.
It will work, right?
You can ask her. I don't know.
No, because the project. Okay.
Ask her. Send her an email.
Okay. So if that works, I can work together. I can work alone, right, on that.
Potentially. I don't know.
Okay, I'll
Ask her
probably
first.
ask her. Yeah.
It's conditional on that. Yeah.
Actually, just one thing. So we were looking at this data from the speech, summary, and other thing. In order to get the data set, having us to fill out this form, and it said it must be technical staff member. I'm not sure why. And even like the signature and all this stuff.
Just email it to me. I'll try.
Okay. Thanks.
Okay. Let's resume. Okay, we're gonna restart in 5 seconds. So, how many people are lost at this point? Lost in terms of what is the objective of this lecture? What is how many people are not clear? What are the few goals of this lecture? maybe I went by too fast. I think one of the students had come by to ask where are we getting to. Okay, so think of a pipeline where you have data. Okay, like for example, here I was saying you have 100 random variables. Just think of them as columns in your Excel sheet. Okay. From those 100 random variables, as in you see the realizations which are going to be rows of your Excel sheet. You can always construct an empirical distribution and draw histograms. Pick two variables, pick one variable, and do all that stuff, right? In fact, you can pick one column and look at the empirical marginal distribution, right? Now, so that's nice. But let's say now you had additional piece of information about how these random variables are related to each other. Okay, we'll get to how we will learn that, but let's say we had information about how these random variables are related to each other. Okay, for example, x could be the income of a person, x1 could be income of a person, x2 could be whether they have health insurance or not, x3 can be whether they are credit risk or not. Different let's say columns. Okay, and you have additional domain knowledge of how these columns relate to each other. And one of the examples I had given a few minutes ago was that, let's say if I index these random variables this way, potentially that I can maybe have additional information that this random variable is conditionally independent of 1 to 98 given 99 x99. Okay, that's an additional domain information that I'm saying, that this random variable is conditionally independent of all these other guys given one particular random variable in this case. Okay, so that conditional information you can think of as, I can encode that type of conditional information. I want a nice representation for that, and that's why we are studying graphs. Okay, and these graphs have to be again tied back to the true original thing, which was the joint distribution. Okay. Now, why do we care about conditional independence information? Why are we trying to encode it in a graph and so on? Is because, as I was saying, if you want to marginalize this, let's say I want to find the probability of x1, I need to do the summation, okay, of 2 to the power 100 numbers. I don't even know how much 2 to the power 100 is, but it's a huge number. Okay, but if you had conditional independence information, then actually the summation becomes very trivial. Actually, it's you can break the summation. You send the this is a huge summation or huge configuration, right? You can actually break it up and actually do it very quickly. Or in other words, what I'm saying is that if you have conditional independence information and you have a joint probability distribution, you can actually compute quantities, actually infer quantities. It's inference problem. You can infer quantities like marginals, conditional distributions, expectations very quickly. Okay, that's the end goal. Without knowing the conditional independence information, I'll have to deal with this object. Okay, which is that vanilla joint distribution with which I have, from which computing things is difficult. So to ease my computation, I want to use conditional independence information, and to get there, we're using this graphical medium, okay, graphical representation to understand conditional independence information and how that relates to the joint distribution. We'll get to actually a couple of examples, 3 examples in few slides. Okay. Right now, on that trajectory, we just looked at, okay, if I had a joint distribution, maybe I can generate a graph this way. That graph, does it capture conditional independence or not? Okay, we saw an example where I said if C is conditionally independent of B given A, then maybe an edge gets deleted. That's what we saw. That's something that we observed for an example distribution. Now we were asking the question, okay, if I have a graph, can I construct a candidate probability distribution? Is it even a valid distribution? That was a question that remained. But we could, somehow, according to some rule, just define some factors, and we could say, okay, this product of factors would be the probability of that configuration. We said we would do that to go from a graph to a joint distribution. Okay, and then we get to this point where we want to say that given a bunch of random variables and a graph, we're gonna tie them together in this notion called the set of random variables respects a graph. Okay, we'll just say that a set of random variables respects a graph, or the distribution on that for those random variables respects a graph if the joint probability is actually equal to the product of every random variable and its condition on its parents. Okay, we're going to now just define this, that P respects a graph if P is actually factorizable in this way. Okay. Okay. So the graph G does not imply that these random variables are conditionally dependent. Okay. What we'll see later in the subsequent slides is that graph is only trying to capture one type of domain knowledge, which is conditional independence domain knowledge, and we'll see how it does that. And the graph G also does not uniquely determine any probability distribution P. Okay, and we'll see that this part right now. Okay, what do I mean by that? Let's say I have a graph G. There could be a P which respects that graph. There could be a P prime which respects that graph. There could be P double prime which respects that graph. By which I mean, when P respects a graph, then the joint distribution decomposes in this way. So there could be multiple joint distributions which all decompose in this way. Is what I'm trying to say. And an example is on the next slide, which is this. Let's say A, B, and C are independent. Okay, so the joint probability is just the product of the individual probabilities. Okay. And so my set X is going to be a set of random variables, capital A, capital B, and capital C. Then X will respect this graph, right? A, B, and C, because according to the rule that we defined earlier, we said we're gonna, for every node, we're gonna have a factor, and which will have the node index itself on the left side, a condition on the node's parent on the right side, but there are no parents for any of these nodes, so I would get these factors. So this set of random variables respects that graph, or this joint distribution respects that graph. It's the same thing. Okay. But you can also see that X also respects this other graph, which is G prime. Okay. Why is that? Yeah, now the C factor has AB as parents, yes. Yeah. Yeah, it's basically a very trivial thing. Probability of C given A comma B is just probability of C. Is that what it's saying? No, I'm just saying that because this identity is true, this graph will create intermediate factors, right? One of the factors would be this, but I know that this factor is just this, right? And so then you get back this. So that P respects this graph. Not clear? No, what do you need to what do you need for a probability to joint distribution to respect a graph, right? You just need to inspect this, right? Whether the product over the factors, right? Which every factor is for a node. Product of the node given its parents, is that equal to the joint probability? Okay. In this case, the joint probability was, because I said, let's say we have additional information that is independent, so it's just this. But anyway, what I'm saying is that here, for this graph, if we follow the rule that for every node we're going to create a factor, then these two are similar to here because they don't have parents. This guy will have parents which are A and B, right? So I'll have this factor there, probability of C given A comma B. But probability of C given A comma B is actually probability of C itself because they are independent. C is independent of A and B, right? There is no conditional stuff here yet. Okay, it's just independence. So that's why I'm saying that if I created factors here, the intermediate factor would be c given a comma b, but I can just replace it with probability of c, and then I get the same thing. So that is the joint. But of course, to get from here to here, I have to use that information that a, b, and c are independent. We did not derive this graph from looking at the joint distribution. I have a graph, I give you a distribution, you're just asking whether the distribution respects the graph. So you're not deriving a graph from the distribution, right? The notion is, you give me a probability distribution, you give me a graph, I'll tell you whether it respects that or not. Whether this is true, because this parents part is from the graph, right? You can just verify this. This is just a verification. Right? Any other question? In fact, we can go one step further. Okay, in graph G prime, it's not saying that C depends on A comma B. That's the point that I wanted to get to. I want to kind of get to the graph representations. So that's the underlying, I guess, not the underlying thing, but that's the key point of these graphs, is that they are trying to capture a certain type of domain knowledge, and that knowledge is only about conditional independence. They don't know about dependence. So if you draw an edge between A and C, doesn't mean that C depends on A. Okay. We'll get to that. I mean, that's just a undercurrent, something that you need to keep in mind. So the graph just says that the distribution of these factors can be represented by the graph G prime. Okay. Sorry, the distribution factors in a way that can be represented by G prime. That's all. And you can also further check that X also respects a G double prime, which is this graph. Okay, I'll just randomly pick some edges. Actually, you can permute them. But what I'm saying is, from this graph, if you just wrote the factors, and since you know that whatever conditional stuff is there, I can get rid of the conditioned part, like the right hand side of this vertical bar. So it is going to, this graph, that distribution will respect this graph. Right? In fact, if you take a complete directed acyclic graph, it's a graph where all vertices are connected to all permissible other nodes, then any distribution on n variables respects this. Any distribution on n variables respects a complete directed acyclic graph with n nodes. So this is actually a directed acyclic graph with 3 nodes, right? Any distribution will actually respect this graph. No, that's not a fact you need to take by faith. You can actually think about it. Why is that? There is no independence here. This is one. I've given you a complete directed acyclic graph. I can't compile that statement. So what I'm saying is, let's just write, right? I mean, let's just go from here to a distribution. I mean, to a candidate distribution. So probability of what is this? C given A comma B times probability of B given A times probability of A, right? What is this? This is just probability of A, B, and C. I did not have any other. So what I'm saying is, for this factors, it just happens that this complete directed acyclic graph corresponds to a degenerate factorization of any joint distribution. Like, basically what I'm saying is, the orientations will determine a factorization, but if you kind of compress it back, it is actually just equal to the joint distribution. So that's what I mean by degeneracy here. So okay, I mean, so what did we say? For a bunch of random variables or a distribution to respect graph G, it just has to decompose it this way, right? Okay, quick aside, we're gonna, although today or in general we are only going to talk about random variables, these things on the nodes of the graph can also be random vectors, collection of random variables. Okay, why is that? Because I can, let's say I have a 3-node graph, A, B, and C, and some orientation. I can always put them together. And of course, I'll have the problem of redefining these edges somehow. Right? But otherwise, I can just merge vertices, right? So what I'm trying to say is, I mean, it could be that you have groups of random variables influencing, groups of random variables related to another group of random variables. If you wanted to capture some information like that, we'll get to exactly what the graph is capturing actually. So I don't want to jump ahead. So what I'm saying is A, B, and C can be vectors, let's say, and same thing whatever we discussed so far is fine. So about this valid distribution that I was asking about, when we, 3 slides ago, we had a graph and we said we're gonna create a factor per node of the graph, and we got some product form, and we were not sure whether that actually corresponded to a joint distribution or not, right? I don't want to flip slides, but let's take it by faith this time that if factors are normalized conditional distributions, then the joint distribution is a valid distribution. Okay. We can, so we had a question here, how many slides ago? Yeah, this was one, right? So from this graph, we just created some product, right? What I'm saying is that this will lead to some distribution, some valid distribution. Okay, that's all. Okay, so what did we do till now? We connected a graph to a joint distribution by talking about this concept of respecting this joint distribution respecting a graph. And I don't know why I put here. So the advantage we'll see is that there's going to be some visualization component, and later on there will be some sampling, or later on the inference algorithms, if they involve sampling, they'll be able to do it efficiently. So we'll get to the second bullet point later, but right now let's focus on visualization. So now I'm going to get to a couple of examples to further drive home the point about a graph and a joint distribution. Okay. And now we're going to slowly introduce the concept of conditional independence as well. So let's focus on linear regression, or the Bayesian version of this linear regression. So here we have xi, yi as the endpoints, n examples in your data set. Let's say xi is d-dimensional, and the model that we're going to follow is a linear model, which is f parameterized by this scalar, okay, or it can, f parameterized by a vector, which is represented by capital W because that vector is a random vector. Okay, don't get confused with the matrix that we had in the first 6 lectures. So let's say the linear model is W transpose phi of x. Okay, where phi is just you can think of it as even just an identity, right? Every x coordinate is just x coordinate. We don't care about it, but what I'm saying is you could have non-linearity here, but it's still a linear model because it's linear in W, right? So I'm going to make some assumptions. I'm going to assume that W is normally distributed, is a multivariate Gaussian with zero mean and variance being only on the diagonal, so there is no covariance, and has a parameter sigma naught square. And I'm going to assume yi as being scalar normal, which is given by W transpose phi of xi with additional variance sigma square. Okay, so that's my model for Bayesian linear regression. So okay. So now we're gonna have to introduce additional information, which is let yi be conditionally independent of yj given w. So two examples, two I guess dependent values or dependent variables values. They are not related to each other given w. If w is equal to some small w, then yi and yj are independent. They are independently drawn from this normal distribution. Okay. So I think the most familiar thing that you might have seen is this, right? If w is grounded fixed parameter, right? You might have seen this, right? Yi is just w transpose x plus noise, so that's why I put it in a normal distribution. Otherwise, this should be familiar to you guys as least squares, not least squares, but okay, linear regression problem. Is that not clear? So in this model that I'm defining with the conditional independence assumption, I'm also going to assume this other things are not random. So first of all, features are not random, and these parameters of these normal distributions are not random. Okay. So the graph corresponding to this specification would look like this. Okay. Where I've just highlighted conditional independence as just this node condition on that. These random variable nodes are independent. Okay. And how many nodes are there? As many as the number of examples. Okay. Because see, w determines y, right? There's a functional relationship here. That's why I've put an edge there. Okay. So this would be a graph representation, a directed graph representation for this specification of my problem. Right. Or the joint distribution actually factors this way. It's the same information that we saw last slide. The joint distribution is just probability of w times the product of yi given w. Okay. This is the conditional independence assumption that we made. And that's why we do that graph, because every node we have a term here. Okay. So here we didn't go from conditional independence information to a graph and then see how it impacts the joint distribution. Here we said we kind of looked at the conditional independence information and directly we can pretty much write this, right? We don't really have to look at a graph for this problem. So that way it's a very trivial graphical model actually. And this part is just saying how do you represent, if you have n examples, there's some notion of plates, so it's just to kind of compactly represent a graphical model when you have multiple copies of things. So in this case, since there are n examples, they're just saying put a square box with n there to kind of represent this graphical model. Otherwise you would have n edges, outgoing edges. Okay. And in terms of there will be additional metadata or additional tag that you add to the random variable. So random variable w will be called a latent or a hidden variable because it's not observed, and y's will be called observed variables. Okay. So this is the joint distribution. Given this joint distribution, you can actually do a lot of things, right? You can actually compute the expectation of w. Sorry, expectation of w. Yeah. If you had access to, this joint distribution or whatever this things, then you can find the expectation of w. You can find the probability of y given everything else, right? But the probability of y given everything else is just probability of y given w. Everything else is irrelevant. So a lot of things you can do if you knew this joint distribution specification, right? Yeah. So that's just a linear regression example. Any questions here? We just really didn't do much with the graph because if I gave you the conditional independence information, you can directly write this pretty much. Okay, let's look at a different knowledge engineering or domain knowledge based graphical model. Okay, so here it's a graphical model where there are 5 nodes. Let's say one node is the difficulty level of a course, second node is the intelligence of a student, and the third node is the grade that the student gets in the course, and let's say stat is the score that the student gets as a SAT score, and then a letter is something that you get based on grade. Okay, a recommendation letter essentially. So this is so you can actually encode this based on domain knowledge, because you know that intelligence is going to determine grade, and the SAT score, maybe the difficulty along with intelligence is going to determine the grade in the class, and maybe the person who writes the letter is only going to write the letter based on the grade. Okay, so these are all random variables because in a particular realization you may be intelligent, you may have a difficult course, so you got a bad grade. Okay, that's all. That's why it's random. So these additional boxes that they have drawn here are actually something that we saw in the review. These are conditional probability tables. Okay, we saw probability tables and conditional probability tables, right? So let's look at this thing, this box here. It's a probability table. Why am I calling it a probability table? Because let's say intelligence is a binary valued random variable. Then it's basically completely specifying that the distribution of that random variable, right? Probability of I equal to 0 and I equal to 1, or in this case I0, I1 are the realization representations here. So probability of capital I is equal to I0 is 0.7, probability of capital I is equal to small I1 is equal to 0.3. Okay, so these two are probability tables, and these other things are conditional probability tables. Okay, and you can see that grade. So here, for example, it's capturing grade given difficulty and intelligence. So difficulty and intelligence are binary valued random variables. So there are 4 options. For each option, you should need to have a distribution. Probability of grade, given that intelligence random variable is taking a value I0 and difficulty is taking a value D0 or D0. Okay. Yeah.
Why is that repeating? Should it be over there I0, D0, I0, D1, then the other thing should be something else, right? Why is I0, D0 repeating?
Oh yeah, it should be I1 here. Yeah, this is what happens when you don't create the slides. Okay. So anyway, so this is a graphical model that was based on knowledge. Okay, we created this graphical model, and the joint distribution is going to be just this, right? Because we said from a graph we can create a factor for each node, and we know that is actually a valid joint distribution. So we can just compute it because we have all the factors explicitly as tables, right? So in fact it's expanded out here. Now what's interesting here is that you can actually now say condition on somebody. So from a joint distribution you can compute 100 different things. For example, from the joint distribution you can say condition on I did not get a letter, and what's my probability of my intelligence, right? What is the distribution of my intelligence, right? Condition on me not getting a letter, what is the difficulty of that course, right? The difficulty of the course, not related to anything else, is just 0.6 and 0.4, but probability of difficulty given everything else, it could be different than what this is. Okay, you can't rule that out straight away, that none of the other nodes are influencing, let's say, difficulty. I mean, you can see that, right? Like, for example, grade is extremely low for everybody, then clearly maybe the difficulty of that course is not 0.6, 0.4, but 0.9, 0.1 or something, right? Very difficult or something. So this is just an example of a graph which is capturing some information. I mean, in this case, just we are only limiting ourselves to conditional probabilities, not conditional independence yet. looking at conditional probabilities and defining these. And in fact, we have captured less. We have only captured these many number of parameters, right? So you already see some savings in terms of parameters. We have 5 variables. So I think other than grade, everything else is two valued random variable. So you have 2 times 2 times, to the power 4, 16 times 3 as the number of numbers that you need to represent this joint distribution. Here maybe you have less than that. Okay. Instead of 16 times 3, which is whatever 48. Yeah, you have less numbers here. Okay. At least you can see that factorization helps in some way. Okay. There's some other complicated example, but we'll not go into this one. Okay. So as I was saying in the linear regression example, some variables that you will never get to observe. Let's say it's a graph of something. Like in the student network, you can observe grade, you can observe the letter was given or not, you can observe SAT score, but you can't observe difficulty and intelligence. So those would be called unobserved, hidden, or latent variables, and then the other ones are called observed variables. Okay. So now we'll get to conditional independence. What is it that the graph is capturing in terms of conditional independence? Okay, because that's what it can capture. As I was saying earlier, it cannot capture conditional dependence. So given a graphical model, or essentially a graph under the distribution, we can determine if 2 sets of random variables are conditionally independent or not. So given the graph, I can tell. So this is a new thing, or pretty much the punchline of this lecture, is that given a graph, I can tell you whether 2 sets of random variables or 2 random variables are conditionally independent or not. Condition on anything in that graph. Okay. So in particular, for example, very simple structure is, let's say you had a graph with just 3 nodes, and you had you want a condition on the node in between. Okay. So because a condition on that node, I've put it in green. Okay. This particular structure is called a tail-to-tail structure because from that node, 2 edges are going out, or whatever number of edges. In this case, in this example, there are only 2 edges which are going out. Okay. For this graph, not for this. Yeah. So this joint distribution respects this graph. Do you agree? We saw the respect concept a few slides ago, right? So this joint distribution respects this graph. Now what happens when we condition on C? Okay. So what happens? Probability of AB given C is just this, right? This is clear. Now we can just substitute probability of AB given C, ABC from here, and you can see that probability of AB given C just factorizes as probability of A given C and probability of B given C. Okay, which just means that AB are conditionally independent given C in this graph. So the graph is telling, so if this was the graph under condition on C, I'm telling you that A and B are conditionally independent if they had edges like this. So just from the graph, I'm reading out a conditional independence statement. Or if you had conditional independence statements, you could encode it in the graph. You can go the other way, but here I'm saying that for this graph, A and B are conditionally independent given C. That you can read off from this 3-node graph. Simple thing, right? You can do the same for a different graph, actually, for a different set of edges. So let's say in this case, C is in between, so it's called a head-to-tail. There's actually different names. It's also called a cascade structure. A head-to-tail structure where there's an edge going from A to C and then an edge going from C to B. Okay. So even here, you can actually see, you can just write the joint distribution from this graph. Okay. Probability of A times probability of C given A times probability of B given C. Okay. At this level, there is no conditional independence information at all. Okay. It's just factorization. When you condition on C, which is that green node, then you can see that again you'll get probability of A given C times probability of B given C. Okay. and that's because I think you switch the order of, so you get probability of A times probability of C given A. You can write it as probability of A given C times probability of C. Okay. And so again, in this graph, you can use the notation A is conditionally independent of B given C. But that's not the case for this 3-node graph. Even so, this is an interesting case. Okay, even for a 3-node graph, what is being captured changes just based on the edges, the direction of the edges. So this is called a head-to-head structure or a V structure. It's just a jargon they introduced. But let's say there are 3 nodes, and in this case, there is this node C, which has in links from its parents, so A and B. Okay. Then for this graph, what is the distribution? It's probability of A times probability of B times probability of C given AB, right? It's just reading of who the parents are. So when you condition on C, you'll actually see that probability of A, comma B given C is not equal to that term. Okay, what we expected. Actually, I should write reset. So since that is not equal in general, so A and B are A and B are not conditionally independent given C. Okay. Yeah, that's the right statement. Okay, the confusing statement which I got confused, which I hope you guys, I will not say that so that you won't be confused. Anyway, so this is a weird structure. Here, you see just with three nodes, you can actually you can infer that they are not conditionally independent. That is also valid information, right? So for example, let's say the head-to-head example is interesting. So let's say A is a Bernoulli random variable with bias half, and B is a Bernoulli random variable with bias half. Then let's say C is 1 if A is equal to B and 0 otherwise. Okay. I flip a coin here. C is just a deterministic function of A and B. That is also a random variable. Function of a random variable is a random variable, right? So condition on C. So if we know A, then we know B, right? And that's why they are dependent, right? Condition on C means when I say C is equal to 1, I know that A has to be equal to B. So if I know B, then I'll know A. So that's why they're dependent. Okay. Similarly, if we know B, then we know A. And so A and B are not conditionally independent given C. Yeah. But unconditionally A is independent of B, that I've just expanded here, but you can actually see that if this is a generative model, then they are independent, right? But they are not conditionally independent. That's all. So that's generalized to something called the D separation criteria. So that was just for 3-node graphs. We're gonna look at, okay, if we had through knowledge engineering, like for example, you saw the student network graph, right? There were 5 variables. Okay, it's not that big. Sometimes you can create, if you've seen some Microsoft products had this Clippy, right? Clippy was a Office assistant or something which used to come up in really old versions of Microsoft Office, right? So that was based on, that is actually an output of a huge directed graphical model, which would look at what's the issue with the user, is he or she able to accomplish the task, it was like they had a huge directed graphical model there. Anyway, so what I'm saying is for bigger graphs, you really need to check this criteria, which is called the D separation criteria or directed separation criteria. So we are looking at larger graphs. So this D separation criteria helps you read off conditional independence properties from any graph, basically. For 3-node graphs, we just saw like there are only 3 orientations of edges that you can have, because head to tail you can also invert it, but it's as good as saying A is the same as B or something like that. So for 3-node graphs, we just saw that okay, conditional independence can be inferred for 2 of the cases, but for the third case we cannot infer. For a larger number of nodes, we're going to just define node sets now instead of nodes themselves. So for example, for this graph, we're going to say, okay, let's this set be A, this set be B, this set be C, and let's say these two belong to B. Okay, and these sets have to be disjoint, and they need not cover all the nodes. So for example, one node is left here. So what I'm saying is, instead of A, B, and C that we saw as these three nodes, in a bigger graph, I can just pull together a bunch of nodes and call it A, pull together a bunch of nodes, call it B, pull together a bunch of nodes, call it C. Right? That's a valid operation I can do. Now, I want to know something about these sets of nodes, right? I can ask one simple question, which is A conditionally independent of B given C? I can do the same thing that we did for just nodes, right? Okay, so for that we need to define something called not define, but we need to say what is meant by getting blocked. So a path between two vertices is blocked with respect to C if it passes through a node V such that, okay, it has two parts. So let's focus on one part now. Okay, a path between two vertices is blocked. So we are now defining that, okay, there's a we know that there's a path between two vertices. Let's say it's connected graph, right? There's always a path. Now it's going to be blocked. We're going to attach a property that is blocked with respect to C. So A, B, and C were the three sets that we created before, right? So it's going to be blocked with respect to C if the path has a node, it passes through a node V, okay, and the node V has some properties. What are those properties? In the first case, the V belongs to C, okay, and the arrows arrows related to the V node are head to tail or tail to tail. So locally, I'm just saying that for that node V, if it is connected as a head to tail or a tail to tail type of a node, then the path is blocked. I'm just defining whether the path is blocked or not. Now that's just a attribute that I'm attaching to a path, right? So let's get to the second part later. So x4, x3, and x2. So here I have defined what A, B, and C are. Okay? Now, x4. So C is so there's only one node in C, right? So let's focus on x4 and x2. Let's say some two nodes. These two nodes, these three nodes are in a head to tail type of structure because there's an arrow coming in and there's an arrow going out, right? So this path from 2 to 4 is blocked. That's all I want to say. Okay. And then okay, I just want the second condition we'll get to later. Okay. Now I'm gonna once I can attach whether path is blocked or not. Now I'm gonna get to our original question, which is to get to our original question there are two steps. One is I'm going to define whether the path is blocked or not. Next I'm going to define whether the sets are d-separated or not, and then I'm going to get to whether they are conditionally independent or not. It's a very simple reduction. First is A and B are d-separated by C if all paths from vertices in A to vertices in B are blocked with respect to C. So I just defined for a pair of nodes there will be a path between them whether it's blocked or not. I just told you in the previous slide. Now for every pair of vertices in A and B, if they are blocked with respect to C, then I call A and B as d-separated. Okay, just this d-separated. It's just an additional attribute I'm attaching to the sets. And if A and B are d-separated, then A is conditionally independent of B given C. Okay, I guess this is not much of a leap there. I'm just saying if there is a d-separated property for two sets, then they are conditionally independent. And this you can do for any arbitrary sets. Let's say you had a graphical, you had 100 random variables. You had a huge graph. Somebody created that domain knowledge based graph, okay, with different edges going to different random variables. You can just pick arbitrarily two clusters of those nodes and try to see if this d-separation property holds. And if it does, then condition on some observation, condition on some variables that if you could observe, then these two variables, random variables, are not related to each other. They are independent. Okay, which is great, right? It's only a necessary condition because even if A and B are not d-separated, I'm not saying whether they are independent or not. So I'm just saying it's an if condition. If they are d-separated, then they are conditionally independent. That's all.
If a single node of a particular cluster is separated from other single node of another cluster, then
Yeah.
the whole cluster will be different.
No. Just those two nodes. So we'll actually, I mean, there is an example here, which is this, right? Let's say C is this, again, X3 only. But now A is this and B is these two vertices, okay? I've just defined A as this. A is the set of one node, B is a set of two nodes, C is a set of one node, okay? Now, the question is A conditionally independent of B given C? That's the question we want to answer, and we can check that by checking the d-separation of all pairs of vertices xi, all pairs of vertices, okay, in A and B. So in A there is only one vertex 5, and in B there is 2 and 4, right? So it's easy to see that 2 and 5, x2 and x5 are blocked by C, because you look at the path from 2 to 5, there is a C in between, and it has a head to tail relationship, and so condition on C we know that. Since it's a head-to-tail relationship, this path is blocked. That much we know, right? And for the second pair of vertices, in this case x4, x5, there is no C in between in that path, so it's not blocked, right? And because these were the exhaustive set of vertices pairs, and since one of them is not blocked, it's not d-separated. And hence we cannot say that A is orthogonal. A is conditionally independent to B given C. Okay. We only have 2 minutes, so I'm trying to figure out. Okay, there's another example. We'll skip that. Okay, it's the same example, same graph as before. We are just looking at different set A, different set B, and so on. Okay, let's one second. Okay, I think actually d-separation is the major point of this. So we couldn't cover the undirected graphical models, but in the directed graphical models, d-separation is the property that we wanted to get to. Okay. Because given a huge graph which may have 100 or 1000 variables, 1000 is nothing, right? I mean, 1000 columns in your data set is nothing. But if you want to kind of capture and somebody, let's say knowledge engineer, some domain knowledge engineer, that this column is related to that column is related to some other column, and so on, somehow created that graph, then like the student graph I was talking, we looked at, and so on. From that graph, you can infer that some columns are unrelated to some other columns given observations of some other columns, roughly. That's what this is translating to. Okay. So the graph is encoding. So when the domain knowledge expert created the graph, he or she has already encoded that conditional independence information, and you can just read that off by just checking for this d-separation property. Okay, and if there is d-separation property, conditional independence properties hold, then you know that if you want to do marginalization or compute expectations or something like that, you don't have to do a summation over all configurations of your random variables. You have 1000 random variables, each is binary valued. There is 2 to the power 1000 potential configurations, and those many numbers you can't really compute. But because of conditional independence, you can do that in within a minute or within a few seconds. Okay, that's the advantage of graphs which encode conditional independence information. Okay, so that's it for today. No summary because there's one more huge section left. Okay, that's it.